Okay, good morning. Can we start? I would like to try to finish elimination today. The other class, the biology teacher class, where some of you, not everyone here is sitting here, is brave in taking this lecture, but some of them escaped because they thought it's probably easier in the other lecture. At least it's in German, but maybe it's easier. But they have already finished elimination, so they are ahead of us. So we have to do something. Now, don't worry, we keep the pace and will not try to compete with this other class. Anyhow, let me give you a summary what I think mechanistically we looked in the moment and where we stand so far. And so for this, let me draw a substrate and let's consider what we have done so far. We looked so far at 1-2 eliminations. What does it mean? That we are eliminating two groups from adjacent carbons. In this case, we are doing HX elimination. The example I'm going to show you is in the moment that we are going to eliminate these two groups, but note that there's also a hydrogen to an adjacent carbon on this methyl group. And what did we look at so far? We looked at the E1 reaction mechanism, in which in the first step the carbocation is forming. And this requires to be that X has to be a good leaving group. So that this can be occur. And then in the second step, loss of a proton by a mild base will lead to the product. Now note here in this moment that, of course, we have free rotation around this bond. So there might be the possibility of geometrical isomers. And in principle, again, also note that we have an adjacent hydrogen from which we could also abstract. So there might be also the possibility for the formation of this product. And generally, this type of reaction is governed by thermodynamic control. And here we have the rule: higher substituted double bonds are more stable than less substituted double bonds. And the other rule we have is trans is more stable than cis. So far, so good. And so in this type of scenario, we would predict that this should be our major product here. And the reality is you get mixtures. You usually obtain, you very often see mixtures of all three of such products under various conditions, but the major compound in general follows very nicely these rules. And then we had in the last lecture at the very end something which followed in E1CB mechanism. And this was basically the opposite here, that the X was a bad leaving group. And then instead of the leaving group, the X leaving first, it's a proton which gets first abstracted. So we go through a carbanion. This is why we have the CB notation here. And this is generally a fast process. And then the rate determining step is that eventually the leaving group is being pushed out by the anion. And again, okay, let me stick exactly with this example here. Will give us the product. And besides that, the X here is a bad leaving group. We have a second requirement here, and this is that this anion has to be able to form, and it can only form if the proton we are abstracting here in the first step is quite acidic. And so therefore, R1 needs to be an anion stabilizing group. And the classical example I gave you for such a reaction in the last 3 minutes of last hour, and this is why I would like to show this to you again, is this kind of product where we try under basic conditions to do an elimination of water, hydroxide being an extremely bad leaving group. It's not going out very easily. On the other hand, the hydrogen next to the carbonyl is acidic because the anion is stabilized as an enolate. And so in the presence of base, even like sodium hydroxide, you form sufficient quantities, concentration of the anion in a fast equilibrium, and still the equilibrium is on the side of the starting material, but nevertheless you build up concentration and then of this, and then in a rate determining step and this is because this is the reason it is still E1, it's not E2, because the base is only acting in the first step, and the first step is not rate determining. And then in the rate determining step, we eliminate our bad leaving group here. The reason I choose this example, and I'm saying it's a classical example, is that this type of compound is an important compound. Does anyone from the basic organic lecture recognize the class of compounds which is behind this? Yeah? This is an aldol compound, right? So this is coming from an aldol reaction. And the aldol reaction we will look at the carbonyl when we do carbonyl compounds. But this is a very common motif which is being formed. And then there's always the possibility to go to the aldol condensation product by eliminating water. And interestingly enough, this does not only work under acidic conditions, where you would protonate the hydroxyl group to make a better leaving group, But this also works under basic conditions because you have the anion stabilizing group here. So classical example for E1CB. Favorite question in oral exams, because Bell's Aldo reaction is something which people like to ask about, and then inevitably it will be asked if we can do the condensation reaction as a second step. Okay, so this was E1 in E1CB, and let's look in the summary also briefly at the E2 reaction. So I just draw the same material I have just written here again. And so in the E2 process, the base is involved in the transition state, but we have last time distinguished between two scenarios, and the scenarios is, again, the question, X, is it a good leaving group? And if it is a good leaving group, we are in the situation that bond breaking, both abstraction of proton and leaving of the leaving group, is occurring more or less at the same time. And again, this usually, it can form the same three products as we have seen above, but again, thermodynamic control suggests, and that is generally observed, that the most stable product is forming. Now, please note again that also in the E2 reaction, and let me put the base here to make clear it's E2. Now, please note again that we have rotation around the double bond. For the E2 elimination, we said it's strictly anti. But anti could also mean that I rotate around this bond and place this hydrogen anti to the X. And then the other isomer, the cis isomer, would be forming. So here you would have a choice. Sometimes you don't have a choice. Sometimes there might be also another substituent here. And there is something where you have to be careful about, that then no matter what the product stability would tell you, for example, if this would be another carbon substituent here and we would do an elimination under E2 conditions, no matter how little these two groups would like to be on the same side, under E2 conditions, they would not have a choice, because you have to place H and X anti to each other as a strict requirement to do the elimination. So be aware of this as well. And then as a variant of this, we had still the E2 process, but where X again was a pretty bad leaving group. So here typical good leaving groups are halides, bromide, chloride, acetate, tosylate. All these are good leaving groups. Bad leaving group, relatively bad leaving group, is we looked at trimethylamine in ammonium salts as leaving groups. And here we have the scenario that the transition state, although again still both proton and X is leaving at the same time, but the transition state becomes unsymmetric. So the X group has really not left by a lot. In contrast to the hydrogen, which is already the bond between carbon and hydrogen here by the base is broken to a much greater extent then the leaving group has formed. And so this transition state, although it is still E2, it's not like the E1CB, but the transition state has anionic character here on this position. And so this is the reason why we observe in general now products which lead to the less substituted double bond simply because hydrogens on a less substituted carbon are more acidic than on a higher substituted carbon, simply because on a higher substituted carbon we have the inductive effect, and of course a donor substituent will destabilize the an upbuilding negative charge. So these were more or less the scenarios we had. We also talked about that the size of the base, of course, can also determine the regioselectivity. The bigger the base, the more it will attack on a less substituted position. But since the protons are, or the hydrogens are more on the periphery of the molecule, very often the size of the base does not so much determine the fate of the elimination as these factors do, which we have discussed here so far. So again, very important, both of these E2 processes we look at here are anti-eliminations, while there's no anti or syn in the above processes, but the anion or the cation which is forming arranges itself usually that the most stable product can be formed. Okay. So now the question, are there Syn eliminations as well? And yes, there are. And Syn eliminations will always occur if you have a reagent which will try to pull out both leaving groups at the same time. So let's look at this example here. Now here I chose a 1,2 dibromide, and we will see again and review this. You all know this, how to make this. 1,2 dibromo compounds you synthesize by adding bromine to a double bond, right? And so let's say you have created this dibromo compound, and such dibromo compounds can be eliminated back to the alkenes by using metals. Zinc metal is very good for this. And the way this works is that the zinc metal basically in the transition state pulls at both of these bromines at the same time, so that once the bonds are broken here, the new double bond can form. And so this way, in this example, which I've chosen here, a Syn elimination occurs, zinc bromide is eliminated, and the alkene is being formed. Now note here, I chose the example in a way that I'm forming the cis product. In principle, there's also a trans product. But because of that reaction mechanism, I do not really have a choice. If I have this dibromo compound as a starting material, I cannot say, oh, hey, I would like to the more stable compound should form. Again, based on the mechanism that it has to be a strict Syn elimination in these scenarios. It has to form, it can only form the cis product, only the product which can occur out of this arrangement. Now, for some reason, you might have had the other diastereomer. So, of course, it could have been possible that you would have had this stereoisomer. So these two are diastereomers. And we will review how you would form by a bromine addition to the respective alkenes either of these. So again, if you would have, for some reason, this one, you would do the Syn elimination. You would now form exclusively the trans product. Because again, it's Syn elimination. And in this arrangement, the R and the two R groups are on opposite sides. So that is how you would find them in the product. And again, you would have no formation of this. Again, this would not be formed. So you see that sometimes in these reactions you can have high stereo control, and also what is interesting is that you start from one diastereomer and come to one product, and you go from the other diastereomer and come to another product. So again, these also here, just to remind you, are diastereomers. And the reaction which occurs like this, where you go from one diastereomer to one defined product, other diastereomer to a different product, such reactions are called stereospecific. So this is an example for a stereospecific reaction. So this is a good example to remember, good example for a Syn elimination. But there is another type of Syn eliminations, and this occurs if you look at such compounds which have an acetate as a leaving group. No. So acetate, let me remind you, on the acetate group, it's the ester of acetic acid. So acetate is a good leaving group. If you treat such compounds with a base, the normal E2 reaction will occur. Following an anti-process, and this will give you, in this case, the trans product here. Now, if you heat this up And I have not chosen the example exactly as I wanted to. So note here, in principle, you again have a second hydrogen. You can rotate. So again, the cis product is also possible. Let me just, for the sake of it, let me put on a different group here to eliminate this possibility. So now the elimination is unambiguous. If it is an anti-elimination, this is the only product which is possible to form here. Now, if you heat these compounds, such acetates, and you heat it pretty high, 600 degrees. We will discuss in a moment how we do this. Then, again, an elimination occurs. But in difference to this elimination, which is E2 anti, now a Syn elimination will occur here. And so let's look what is being possible to happen here. See that I do this. The elimination of the acetate group will occur from a Syn transition state. And the reason for this is that the acetate can more or less act as its own base. And so the proton here can be abstracted by the acetate group. And then, if this goes in here, and this breaks, this is what is being formed. And in this case, you would form this product. And this type of transition state is very good. It's, first of all, as I said, it makes somehow sense. We have some kind of a atom here which can act and assist the proton abstraction. But if you look at this transition state which I have drawn here, something might occur to you why this is a particular good transition state. Anyone an idea why this is very good? It's almost as magic as the octet rule, where 8 is the magic number. In transition states, very often, 6 is the magic number. And why is 6 the magic number? 6 electrons dancing in a circle with each other. What does it remind you of? Yeah. What is it? Diels-Alder reaction is, again, a reaction where we have a 6-member transition state and 6 electrons dancing in a circle. That's okay. But what's behind this? What is the compounds we know to be particularly stable, where we have 6-membered rings and 6 electrons in there? It's aromatics, right? So this type of transition state is a transition state. It's an aromatic transition state. So look at this. It's basically, it resembles somehow an arene, right? We have, in this case, even 6 atoms. We will see in a second it does not always have to be 6 atoms. But more importantly is we are moving 6 electrons basically in a circular direction, always alternating here forming a new bond, breaking a new bond, forming a new one, breaking the bond, forming the bond, breaking the bond, forming the bond. So we do it exactly alternating, and we have exactly an alternating situation as we have in benzenes. And so this is particularly good, and this is why these reactions occur. Nevertheless, you see pretty high temperature, 600 degrees. Now, organic molecules are usually not very happy at 600 degrees. So the question is how to do this. And the technique you use here is the technique to do a so-called pyrolysis reaction. And what you do is you have an oven. And in this oven, you have a tube. And so this oven you can heat at 600 degrees, and you can do even higher. Many of these pyrolysis apparatus do 1,000 degrees and more. And then you have your flask here, and the flask has your compound. And then you have a second flask here where you collect your product. And typically what you have to do is you cool this down at in an ice bath or something, very often solid carbon dioxide, minus 78 degrees, you cool this. And now what you do is basically very slowly you put on a vacuum line here, and you very slowly sublime or distill your compound through this tube here. And although it is very, very hot in here, the contact time is milliseconds. So it just runs through this tube very quickly. And so this way, although this looks like an extremely high temperature, it's a very mild method. It's actually a very good method to convert organic molecules in this way. And such reactions are generally very, very clean, much cleaner than such a base-induced E2 reaction. And so acetates do this, but a number of other compounds do this as well. Compound, starting material, substrate, whatever. If anyone ever wants to see such an apparatus, I think we have one in our group, right? Elena, we have a pyrolysis apparatus in our group. We do this from time to time. There are variants to this acetate pyrolysis. We talked already about xanthogenates when we talked about radical reactions and desoxygenations. remember that when we talked about tin catalyzed or tin mediated deoxygenations, we were forming such xanthogenates. And these compounds, and you see the analogy, it's basically just a sulfur atom here. In the acetates, we had an oxygen. Again, these do the very same type of Syn elimination process. And form these type of products. This is something which occurs already at slightly lower temperatures. So the xanthogenates are more reactive for this type of process. And the third class which is doing this are so-called N-oxides. You don't see this too often, but still I would like to show this to you. So in a situation like this, we talked already about leaving group when we had a trialkyl ammonium group here. But such types of N-oxides can also be formed by oxidizing amines. And now again in a very analogous type of reaction, you do the Syn elimination and eliminate this hydroxylamine type derivative. And again, this is something which occurs below 300 degrees already. So these are the most reactive type of compounds. The reason I showed this to you is look at the transition state here again. So in this case, 6 atoms are involved. Cyclic rearrangement of 6 electrons, but it's a 6-member transition state. Now look at this here. 1, 2, 3, 4, 5. We have only 5 atoms in the transition state, but we are still having 6 electrons moving around. So that is, again, keep in mind what makes an aromatic transition state is the movement of the 6 electrons. It does not have to be a 6-membered ring. It can be a 5-membered ring. And of course, we all know that there are many aromatic systems when we have heteroatoms like pyrrole, which are also aromatic, but they only contain 5 atoms in the cycle, right? So again, the question of aromatic transition state or not is the question, do we have cyclic movement of 6 electrons? And this can occur in 6-membered rings. It can occur in 5-membered rings. Okay, so we have 6 more minutes. So let me just tell you a story. So the question is there something more than 1,2 eliminations? What about 1,1 elimination? And indeed there are. From relatively simple compounds, you might already know. Chloroform. If you treat chloroform with a strong base, sodium hydroxide, has to be concentrated, 50%, as concentrated as it gets. But if you treat this then also an elimination will occur, but this time it will occur from the same type, the same leaving group, and this is the same center, and this is why it's called a 1-1 elimination, because HCl will leave, in this case, from the same atom. It's known that this process was studied a lot. It's known that it is a two-step process where this anion formation is in equilibrium and relatively fast, but then indeed the reaction will continue and the chloride will go out, and you're forming a species like this. Does anyone know how these are called? What is this for species? Carbon with only two groups. We could call it unhappy carbon, right? But there are many unhappy carbons, so this is called a carbene. And these carbenes are highly reactive. So these are very short-lived intermediates, but they are extremely useful. And 150 years ago, it was discussed if such species could be stable or could be formed. There was a professor who came in the lecture and said, I solved the problem. And he brought a bottle which had a clear liquid in there. And he said, I made dichlorocarbene, and here it is. And he put the bottle with the liquid in there and said, I got it. At this time, there was no NMR, there was no spectroscopy, there was only elemental analysis. And he said, I did the elemental analysis, and I had the composition 1 carbon, 2 chlorides. And he said, so you see, there is stable 2-bonded carbon. Of course, a carbene is so highly reactive, if it does not find anything to react, it will react with itself, because this is a 6-electron species, and so it will do dimerization with a second carbene. And so it forms, in this case, tetrachloroethylene. This is, of course, a very stable, clear liquid, and this is what the professor brought in his lecture. And, of course, the elemental composition, as you see, 1 carbon, 2 chlorides fits perfectly. But what is much more useful is that you can react carbenes in the presence of excess of alkenes. And what this will do is that the alkene attacking the carbene, but at the same time, this lone pair from the carbene is attacking the double bond. And this way, what you're forming is a cyclopropane. And so carbene additions to alkenes to form cyclopropanes is a very important reaction. There are many famous drugs which have cyclopropyl moieties in it. Ciprofloxacin, the famous bioantibiotic, for example, has a 3-membered ring, and there are many, many more. So this type of reaction is very important. Best way to make cyclopropanes is going through carbenes, and a very good method to make them is from very inexpensive starting materials. Chloroform, you know this as a solvent, and all you need to do is react this with sodium hydroxide, and then have at the same time your alkene already present and in excess, so that you can trap the forming carbene immediately. Okay, This is about 1-1 reactions. We will continue a little bit on eliminations, but very little more, and then start with addition reactions. Hope you have a very good weekend.